Since more than 70 years, natural antibiotics have worked as the most effective micro-warriors that modern medicine can offer. They are small molecular structures provided by nature with successful strategies to kill infectious bacteria or pathogens. Some break their cell walls, others attack their RNA. When bacteria's worst nightmare was found, it soon became very common to use these antibiotics on almost every occasion. Combating both deadly diseases and minor infections, antibiotics were given to humans as well as to animals, actually to everyone, until bacteria got used to them, evolved and became resistant. Our hospitals are boot camps for pathogens. Hordes of sick people in a crowded space, weak immune systems, strong medication. That's the combination which makes them tough. With every new bacterium, with every new form of resistance, a stronger antibiotic has to be found, still able to kill the deadly bacteria. And this competition is not a fair one at all. Infectious diseases use mutation to modify their DNA from generation to generation. Antibiotics cannot do this. There is a limited number produced by nature, and this limited number may soon come to an end. Today, doctors around the world are in fear of the superbug, a strain of bacteria able to resist every antibiotic in our arsenal. It is not a question of whether or not, the question is, when will the first superbug appear? So what if nature cannot provide useful antibiotics anymore? What opportunities do we have to combat a raging superbug? Of course, we call the SYNMOD Team. The SYNMOD Team has a promising new approach to solve this problem. They use synthetic biology to try to produce new antibiotics that cannot be found in nature. And this is how they want to do it. Some antibiotics consist of a combination of so-called peptides. Depending on their genome, bacteria and fungi produce and combine these peptides to form proteins. The way the peptides are combined decides if a protein works as an antibiotic or not. Nature is currently only providing a few combinations, but practically their number is almost endless. Endless combinations could mean endless numbers of new antibiotics. Using modular peptide parts, almost any combination could be developed. The power of modularity and combinatorics could now work together to help SYNMOD to find the desired molecules.
So the SYNMOD team consists of different research groups over whole Europe. There's one group in Groningen which is involved in peptide design, so they design the novel antibiotics. There's one group in Regensburg which is involved in the synthesis of these novel antibiotics. We here in Basel are involved in the identification process. Another group which is involved in the project is Tübingen. They are designing a production platform to get a high-level production of these novel antibiotics. And finally, our partner in London is involved in the design of a perfect media composition for the growth of these production platforms.
Anyway, this method is a little bit like joining a big lottery game. Every combination could hit the jackpot and create a new antibiotic. But in fact, only a very few do in practice. Because of this sad fact, SYNMOD does what the average gambler can't. It places thousands of bets. Placing so many bets means to produce very large amounts of new peptide combinations. Engineered bacteria can do this job very efficiently. For example, Staphylococcus carnosus. This bacterium, let's just call him Staph, is well known and works in sausage factories around the world. But Staph can do much more than just the sausage business. Staph has a genome that can be easily modified, and so he can create the desired peptide combinations. This is why he will be hired by SYNMOD. Working as a production unit, staff will generate large numbers of new proteins. And some of them may have antibiotic properties. In a lottery, when the lots are drawn, people have to check their tickets, hoping to be the lucky winner. As SYNMOD has produced some thousands of molecular tickets, it is impossible to check each one individually. This is why the whole process of production and testing is done in one step. SYNMOD will use nanoliter reactors that are more or less tiny drops of solvent. Every protein-producing staff unit is put in its own microreactor, together with other bacteria, the potential victims. Each time that staff manufactures harmless proteins, the other bacteria will grow, and the microreactor will be filled with new target bacteria. But once staff produces a viable antibiotic, bacteria will be killed and leave the reactor empty. If the SYNMOD strategy succeeds, the race is on again, and weak antibiotics can be replaced by new ones, fighting the new resistant strains of bacteria. The principles of modularity and combinatorial power could also be applied to other research and development efforts in biotechnology. SYNMOD can be compared to a time-lapse evolution program, giving human civilization a head start.